begin the first row of what's going to be the cell body. And now I'm going to go off and make a dendrite on each side. So I'm going to string 4 more of the beads that I'm using for the dendrites. So there. So you've got a cell body with dendrites, receptors at the end of the dendrites.
So what, could you show me a synapse?
It's a gap between.
I can. You want to show it? Should we show it?
So that part, which are the,
Terminal.
would get very close to the
Dendrite.
dendrite. And that area, the gap in between would be the synapse.
Oh, okay. I want you to throw them down on the floor over here and then gather around the place where we're throwing them down. All right, are they all down? We're coming close. So what does this represent with our grouping of neurons here on the floor?
Neurons throughout our body.
The neurons what?
The neurons as they communicate throughout our body.
All right, so this might look like the placement of neurons in some subsection of the nervous system, in the central nervous system, where they're packed very close together, where axons and dendrites might not have any specific orientation in a laminar pattern. They just are on top of each other and connected in some kind of a way. Can we, as they've fallen here, trace any pathways, communication pathways from one neuron to the next? Okay, which way is information flowing between those two? It goes from the purple cell body and the blue axon to the green and clear dendrites and the pink axon. So certainly this blue-purple could be synapsing over on this yellow one if we move it a little bit. But it was very interesting because we have here the nerve terminal from this black cell body, white axon, coming right up against the nerve terminal from the pink with the purple axon. So we've got 2 nerve terminals, 2 axon nerve terminals coming together. Is that a site where we normally would see synaptic activity? No. We teach that the nerve terminal synapse is on the dendrite. How is biology like the English language? Crazy, what else? There are always exceptions to the rules. In the central nervous system, even though we're teaching your students that nerve terminals synapse on dendrites, and information flow is from the input dendrite end to the axon terminal output end, you can have what we call axonic synapses, where this black nerve terminal may be synapsing on the pink nerve terminal and causing changes in that nerve terminal and how it might release its neurotransmitter onto another cell that might be in the way. Okay, or they're ready. So here's an axodendritic synapse and there's an axonic synapse.
And will that happen only if there's one of these nearby, or it could happen to just, so it would stop then?
Right, so
something else has to be-
you still need something to complete. Or if you don't have another neuron to receive the signal, then you have to have a muscle or a gland. A neuron who just has no place to synapse isn't happy. It doesn't like that. It doesn't like not having a connection. And what happens is it either retracts these and goes someplace else, Or under some conditions, it might retract the whole thing and die because it doesn't have any use. All right, so in the neuron, we have a small electrical signal that's generated in the dendrite when that synapse is active, and those small electrical signals add up in the cell body. So it sums all of the incoming information, and here we've got it only giving one, but maybe we can get some more information coming in. We connect a few more neurons here. All right, so now it can add up all of the signals from all of the incoming sources. When it reaches its threshold, it will send its own electrical information as an action potential down its axon to its nerve terminals, where the electrical energy can't go any further. What happens when the electrical energy can't go any further?
Neurotransmitters.
So there's a release of a chemical we call a neurotransmitter that jumps across that space or kind of diffuses into that space, binds to the receptors on the dendrite that's right there, the apposed dendrite. Those receptors get activated, cause a change in membrane potential in the dendrite, and that creates a new signal that goes to the second cell body, the postsynaptic cell body, to sum it up, and the process begins again.
Could someone tell me we talked about a fingertip. Is there one part on here that I could point to and say, ooh, a fingertip?
There.
Here?
There.
Okay, so here's a fingertip.
Can you trace the path for me from the fingertip?
If I kick someone in the finger, what is going to happen? If I kick them here, how is the signal going to travel to make them say, ouch?
It's going to go 2 ways.
Ooh, you see 2 ways?
What's faster, the movement of electrical signal within a cell or the communication across a synapse? Usually the length of time it takes for the information to move through a cell electrically is much, much quicker than across a synapse, because just biologically, and we'll look at it, all the machinery you've got to get together to spit out that chemical is a lot of protein-protein interaction. That takes some time. There's some physical boundaries there. There's a lot of movement that's got to occur.
Now, when the energy flow through this, I'm just looking at it, and that way would the energy follow the path of least resistance? It doesn't matter, they would just all react at the same time, at the same way?
Well, it depends
Or would one
on...
impulse overtake another?
All right, so what happens when this green, white, and red neuron receives input from the set of neurons that I now have synapsing on it? What kind of rhythm might one expect or not expect from the incoming cells? Would they necessarily be firing simultaneously? No. Would they necessarily be firing in some kind of an ordered sequence? 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. No, chances are they're firing randomly. Or they're activated by other parts of circuits that might be firing in a proper fashion. So this green, white, and red cell is going to receive input whenever it comes in. And if they come in simultaneously, temporally, from 2 different sources, that will have a bigger impact postsynaptically than if they are asynchronous.
Can it ever take in too much and like you fry it out?
No, because once you've reached threshold, then another arriving piece of input is not going to do any
And
more.
it would just make more terminals, right?
If there is a lot of activity going on, the pathway's used a lot, there might be an increased synaptic strength, they might make more nerve terminals, that connection might get strengthened.
Aren't some neurotransmitters inhibitory and some excitatory, and they send different messages anyway, so then it would just depend on what's being released?
Oh, very interesting. What happens in the circuit we've laid out if this pink and yellow and white neuron is releasing neurotransmitter that is an inhibitory neurotransmitter as opposed to an excitatory neurotransmitter?
Gets confused.
All right, so if the release of an inhibitory neurotransmitter onto this last neuron in our chain, we'll take the membrane potential here and we'll move it away from threshold. It will hyperpolarize it or make it more negative. and make whatever signal comes in through the longer pathway, if this is an excitatory signal, will have to be stronger, or there'll have to be more of it in order to move the membrane potential back to threshold. So basically, this green cell body is summing up that input. And so if you get a -1 from here and a +1 from here, nothing might happen. If you get a -1 from here and a +2 from here, you might have a net movement far enough up to get threshold. And I'm just picking numbers out of hats, but you have to think about it in that kind of summation fashion. What about the black neuron with the yellow dendrites that was the second output from the multicolored one? Let's continue to trace that pathway.
So that goes
That's right.
up to here
It comes back. Where is it? Where is it synapsing?
with this one.
Okay, so it's synapsing on the original yellow neuron with the blue and red dendrites. So that's kind of curious that it goes backwards. What might that be?
Is that a feedback loop?
That is a feedback loop, absolutely. And neurons do that all the time. They send the same information back to the beginning for reconsideration and reassessment. Short circuiting. All right, so let's make a longer circuit. So let's look at the circuit starting at the blue and white neuron here. In fact, we can even put one upstream. So we've got direct connection here. What happens to the output of this blue, white, and green neuron? Where does that output go? Two different places. So that information is branching. It's going two places. Where is it going? Which is the longest path it takes? Okay, so it goes from this nerve terminal to the yellow and pink, and from the yellow, pink, and white, it goes to the green, white, and red. All right, this is our last one in the circuit. So that's 1, 2. What about the other path? On this side, there's 1, 2, 3 neurons before 4 you get here. So this is the longer pathway. If we start with the signal here, and we look at the output, or what is received in this green, white, and red neuron, which way is the signal going to get to here quicker? Through the shorter route. So that's essentially a short circuit. It's actually called feed forward, because the information that's coming the long way gets there more quickly through the shorter path.
The neurons in the brain, is there a set, there's 10 to the 11th of them eventually. So is there a set pattern for them? I can't imagine that there would be. Is there, you have all these connections.
So
yeah, they place, is it random? The cells just divide until a certain point?
All right, so cells are dividing along the neural tube, more at the head end than at the tail end. So you get lots of cell proliferation, and they migrate. They migrate based on chemical gradients that they sniff or smell. Usually there's one axon that finds its way first, and then multiple others follow along behind it, because neurons like to stick to neurons. And so it's easier to stick to each other and follow the one that got there first. And they can usually find where they're going in embryonic brain reasonably quickly, because things are close together. And then as the whole structure grows, those axons elongate and the connections stay in place. But how things actually find their targets, even within the complexity of the central nervous system, is still very much a forefront of research. So there are people actively saying what genes get turned on that make cell X sniff out cell Y. All right, neuron X and neuron Y. So there's lots of signaling for finding the right places in development that we don't understand at this point, because these brains all do look alike. You saw how similar the different sheep brains looked. And the sheep brains don't look that different from human brains, other than size and maybe a little squish. Okay? Some areas are more developed in humans than in sheep, but all mammalian brains have quite a lot of similarity. So what is it about them that makes them always look the same? And those are growth signals that we have to figure out, or we're trying to figure out. What other kinds of connections do we see here on the ground?
Is there a dendritic-dendrite connection that regulates the signal coming in?
I love it. Dendrodendritic synapses. Can we have dendrodendritic ones? Now that we've broken one rule, yes, the answer is yes. They're much more, there's even fewer dendrodendritic synapses. They really only happen in the olfactory bulb. So that's, not only an exception, it's an exception that only happens one place. So that's much less common, is dendrodendritic synapses.
For instance, I've never learned a foreign language. Okay, never had to. For me, if I started to learn it, I would speak with, I have an accent when I speak English anyway, but I would have an accent, a thick accent, on to whatever foreign language I'm learning. But if I would have learned it as a youngster, I would have a better chance of not having an accent. Correct?
True. All true.
Okay, so for me to learn a foreign language right now would be much more difficult than me at the age of 5. Right?
Yes.
So, but the activity level of my brain, if I learn it now, would get much stronger. Correct?
The same things we're talking about would be occurring in your brain now as when you were 5 in terms of making connections to learn that language. Unfortunately, the plasticity that we talk about in terms of making and unmaking synapses is, for lots of reasons, is much greater in infancy, toddlerhood, youth, even adolescence, than when we get to be multiple decades old. All right.
Post-puberty, I think now has been the latest language research.
So that lack of plasticity has to do with things we don't understand about general aging, and the fact that once we get myelinated axons in place, that myelin tends to make it harder for lots of axonal growth to new places. So some of it has to do with the nervous system getting that myelin in place and being set in its ways. But you still make new myelin even at my age. So you can, and hopefully will, learn new things.